Welcome to SS2 Physics, Term 3, Week 10. Quantum theory is the framework that describes the behavior of matter and energy at the atomic and subatomic scale. It is arguably the most successful physical theory ever developed. Its predictions have been verified to greater precision than any other scientific theory. By the end of this lesson, you will explain Bohr's model of the hydrogen atom, describe energy levels and electron transitions, calculate photon energies using the energy level formula, explain the laser principle, and answer WAEC questions on atomic physics and quantum theory. Let us begin. When atoms are excited by heat, electrical discharge, or light, they emit light. But unlike the continuous spectrum from a hot solid, excited atoms emit light at specific discrete wavelengths, a line spectrum, emission spectrum. Each element has a unique line spectrum, like a fingerprint. Hydrogen's visible line spectrum, Bohr series lines at 656 nanometers, red, 486 nanometers, blue-green, 434 nanometers, violet, 410 nanometers, violet-ultraviolet. Rutherford's nuclear model, 1911, could not explain these discrete lines. According to classical physics, electrons orbiting the nucleus should continuously radiate energy, like any accelerating charge, and spiral into the nucleus in about 10 to 11 seconds. Atoms clearly do not collapse. Bohr's model of the hydrogen atom, 1913, proposed that electrons occupy specific allowed circular orbits around the nucleus, stationary states. Key postulates: 1. Electrons can only exist in certain allowed circular orbits with specific energies, quantized orbits, while in these orbits, electrons do not radiate energy. 2. Electrons can jump from one orbit to another by absorbing a jump to higher orbit, or emitting a jump to lower orbit, a photon of exactly the right frequency. Energy of photon equals difference in energy between the two levels, HF equals E_upper, E_lower, emission. Energy levels of hydrogen, N equals -13.6 N superscript 2 eV, where N equals 1, 2, 3, 4. Principal quantum number. N equals 1, ground state, lowest energy, E1 equals -13.6 electron volts. N equals 2, E2 equals -13.6 divided by 4 is equal to -3.4 eV. N equals 3, E3 equals -13.6 divided by 9 is equal to -1.51 eV. N equals infinity, E equals 0, ionized, electron completely freed. Ionization energy, energy to remove electron from ground state equals 13.6 electron volts for hydrogen. When an electron drops from an excited state, N equals upper, to a lower state, N equals lower, it emits a photon with energy equal to the difference between the two levels. HF equals E_upper, E_lower equals 13.6, 1/n_lower superscript 2, 1/n_upper superscript 2, eV. This is the Rydberg formula. Series of hydrogen spectral lines, Lyman series, UV transitions to N equals 1, ground state. Bohr series, visible plus near UV transitions to N equals 2. Paschen series, infrared transitions to N equals 3. Bracket series, far infrared transitions to N equals 4. Only the Bohr series falls in the visible range. When an electron absorbs a photon of exactly the right energy, it jumps to a higher level. This gives the absorption spectrum, dark lines at the same wavelengths as emission lines. Worked example: calculate the wavelength of light emitted when an electron in hydrogen falls from N equals 3 to N equals 2. E3 equals -1.51 electron volts, E2 equals -3.4 electron volts. Energy of photon equals E3, E2 equals -1.51, -3.4, equals 1.89 electron volts. Convert to joules. 1.89 times 1.6 times 10⁻19 is equal to 3.024 times 10 to 19 J. E equals hc/lambda. Lambda equals hc/E equals 6.626 times 10 to 34 times 3 times 10, 3.024 times 10 minus 19 is equal to 6.576 times 10 to 7 m equals 657.6 nanometers is almost equal to 658 nanometers, red. This is the red line in the Balmer series, the H-alpha line. Consistent with the observed value of 656 nanometers, confirming Bohr's model for hydrogen. Laser stands for light amplification by stimulated emission of radiation. All light from ordinary sources is emitted spontaneously. Atoms emit photons at random times and in random directions. In a laser, a population inversion is created, more atoms in an excited state than in the ground state, achieved by pumping energy into the medium using a flash lamp, electrical discharge, or another laser. 2. Stimulated emission occurs. A photon passing through the excited medium triggers excited atoms to emit identical photons, same frequency, phase, and direction, amplification. 3. The emitted photons bounce back and forth between two mirrors, the optical cavity, building up a powerful, coherent, directional beam. The output laser beam is monochromatic, single wavelength/frequency, coherent, all photons in phase, collimated, all photons in same direction, very intense. Laser applications: medical, laser surgery, eye correction, LASIK, cancer treatment, cutting tissue with minimal bleeding because the beam cauterizes as it cuts. Communications: fiber optic cables use laser light to transmit data at nearly the speed of light. The internet depends on lasers. Industry: laser cutting and welding, laser printing, barcode scanners. Science: laser cooling of atoms, atomic clocks, measurement of distances, LiDAR. Military: laser rangefinders, controversially, laser weapons. Other quantum technologies related to atomic energy levels: LED, light-emitting diode electron transition in a semiconductor junction emits photons when forward biased. Fluorescent tubes: mercury vapor excited by electrical discharge emits UV. UV excites phosphor coating which re-emits visible light. X-rays, discovered by Wilhelm Röntgen in 1895. Production: electrons are accelerated through a high potential difference, 30 to 150 keV, and smash into a metal target, tungsten. Two mechanisms produce X-rays: Bremsstrahlung, breaking radiation. Electrons decelerate rapidly on hitting the target. This deceleration releases photons of a range of energies, continuous X-ray spectrum. Characteristic X-rays: the incoming electrons knock inner shell electrons out of target atoms, outer electrons fall inward to fill the gap, emitting photons of specific energies, line spectrum, unique to the target metal. Properties of X-rays: high-frequency EM radiation, lambda equals 10 to 10 to 10 to 12 m, highly penetrating, ionicing, travel at sea, diffracted by crystal lattices. X-ray diffraction, used to determine crystal structure, including the structure of DNA by Franklin, Watson and Crick. Medical uses of X-rays: imaging bones and dense tissue. Bones absorb X-rays, appear white on image, CT scans, computed tomography, 3D X-ray imaging, cancer treatment. High-dose X-rays destroy cancer cells, radiotherapy. Hazards: ionizing radiation damages DNA, causes mutations, cancer, minimized by lead shielding, minimal exposure time, lead aprons for patients. X-ray diffraction: when X-rays hit a crystal, the regular atomic spacing, typically 0.1 to 0.3 nanometers, causes diffraction. The wavelength of X-rays is comparable to atomic spacings. Bragg's law, 2D sin and theta equals n lambda, used to determine crystal structures. Key points: Bohr's model: electrons in hydrogen occupy quantized energy levels n equals -13.6/n superscript 2 eV. Electrons emit photons when dropping to lower levels, HF equals E_per, E_lower. Hydrogen spectral series: Lyman, UV, to n equals 1, Balmer, visible, to n equals 2, Paschen, Raya, to n equals 3. Line spectra are unique to each element, spectroscopic fingerprint. Laser, population inversion plus stimulated emission plus optical cavity coherent, monochromatic, collimated light. Laser applications, eye surgery, fiber optics, cutting/welding, barcode scanners. X-rays, produced by high-energy electron bombardment of metal targets, ionicing, used in medical imaging, CT scans, radiotherapy, crystal structure determination, X-ray diffraction, Bragg's law. WAEC tests on quantum theory, energy level calculations, photon wavelength/frequency from energy level transitions, ionization energy, describing laser principle, X-ray production and uses.